Okay, so 8.1, a sequence actually has a formal definition, and it's still a function that maps one thing to another. You have an input and an output. So a sequence is still a function. And the domain, remember domain stands for X. The domain is actually the term number, and they're consecutive integers, 1, 2, 3, 4, all the way up to n. That's super important when you're trying to find the rule for a sequence, that you're basically mapping these numbers onto the term. One, what do you do to 1 to get a sub 1? What do you do to 2 to get a sub 2? And these subscripts are, I'll make this a little bit bigger. The subscripts are the terms, the first term, second term, third term, fourth term. And this actually shouldn't be n, it should be a sub n, exactly, a sub n. Yeah, so you generalize it. So eventually you want to take n and map it onto a sub n. And that's the rule for the sequence. So the values in the range are called the terms of the sequence, terms. So we have the domain is the term number, and this is the actual term. So this is like the term number, and this is the actual term. That would be the most concise way to say it. And then this will become more important later, but there's two types of sequences. You can have arithmetic and geometric, which we touched on last time, and we'll review it again. But you can also have finite or infinite. And it's not going to be as important today, but later it will when we're doing series. But just so we have the vocabulary, it could be finite or infinite. So usually you see the ... for infinite. And then there's two formats for expressing a rule that you might see. So I just want to show you both of them. You might see, so for example, 2, 4, 6, 8. Obviously, you're multiplying the term number by 2, right? And that's how you get 2, 4, 6, 8. So the rule is 2n. You might see a sub n equals 2n, or you might see it as function notation, f of n equals 2n. But those mean the same thing. So let's practice. One of the skills is just expanding, writing out the terms. This is the easy direction. So like for a sub 1, you literally plug in 1 whenever you see an n. So this would be 2 times 1 plus 5, or 7. And then this would be 2 times 2 plus 5, which is 9. And this would be 2 times 3 plus 5, 11. And you kind of get the hang of it, that it's then 13, 15, and 17, right? But there's something more important I want to say about it, because we're going to have to go in the reverse direction. So if I were given the numbers 7, 9, 11, 13, and I asked you to write this rule, what do you notice by expanding it that would tell you the 2? Where does the 2 come from? That's the common difference between these terms is the 2. Notice it's not n plus 2 though, right? You actually multiply times 2. And that means that the common difference is 2. But in the rule, it's 2n. It's not n plus 2. Because you can see it right here when you expand it. 2 times 1, 2 times 2, 2 times 3. So it's multiplication. And then where do you think the plus 5, if I'm trying to go in the reverse direction, Michelle? Yeah, the 0th term would be 5. So if you, instead of adding 2, if you wanted to go back the reverse way to get a sub 0, you would subtract 2, right? And you would get 5. A sub 0 equals 5. And so this is the formulaic way you can always find it whenever you have an arithmetic sequence, meaning you have this common difference each time. Like you're adding a constant, 2, which is 2. So whatever constant you're adding, that is times n. And then the 0th term, if you back up one more time, will give you the it's like the, does this remind you of anything? 2n plus 5? Yeah.
Like the slope, mx plus.
It's exactly the slope and the y-intercept, exactly. So 2 is like the rate of change, and then this is like the y-intercept. Perfect. Okay, so let's try this one. You plug in -1, -3 times 1 minus 1, which is, we have to be a little bit careful here, -3 to the 0. Review of exponents. When you raise any number to the 0th power, it is always equal to 1. Yes. And then we have f sub 2. So that's 2 minus 1. So basically you can see you're doing the powers of -3. So -3 cubed, etc. So is this, do you remember the name for this when you're multiplying by a constant? Because we're always multiplying by -3. Let me write it out first. So you get -3, and then -3 squared is positive 9, and then -3 cubed is negative. So see how you're alternating signs? You're always multiplying by a negative number. And we'll talk about how to find the rule always for that. But do you remember the name for it when you're multiplying by a constant? Yeah.
Geometric.
Yes, nice. Geometric. Okay, and we're gonna save geometric for next time. But we have a couple more things to talk about. What about how do we find the pattern if it's neither arithmetic or geometric? So, for example, this sequence, -1, -8, -27. You can see that there's always a negative in front, so that's easy to take care of. We want to find the rule, so I want to know what a sub n equals, and I want to write it in terms of n. But compare, n is 1 here, 2 here, 3 here, and 4 here. So how do we go from these term numbers to get these? And it's not completely obvious. Because but it is obvious that we're not adding a constant. It's also obvious we're not multiplying by a constant. There's something more happening. Yeah. You, Roxana?
It's like negative n parentheses cubed.
Good. So these are the perfect cubes. So when in doubt, so perfect squares are like 1, 2, 4, 9, 16, 25, 36. You should kind of have those numbers in your head. Perfect cubes are 1, 8, 27, 64, right? So it's saying 1 cubed, 2 cubed, 3 cubed, 4 cubed, right? So the formula is n cubed, but then we can tack on a negative in front, and so that will work. And you can also, I think this is what you're gonna say, it will also work if you put the negative inside. Is that what you're gonna say?
Yeah.
Yeah, because when you cube a negative, it stays negative. So either one is perfectly acceptable. It works. So it's fine either way. So let's try this one. Now, fractions, the tip here is you can do the numerator and the denominator separately, because otherwise this is going to be very hard to find a rule for. So let's treat it like two separate problems, and we could probably go directly to the answer. Remember, we're comparing. If it helps you, write out the sequence, the term numbers, and then you're comparing. So let's just do the top. How do we go from 1 to 2, 2 to 4, 3 to 6, 4 to 8? We're multiplying by 2. So the numerator is taken care of. It's 2n. What about the denominator? 1 to 3, 2 to 4, 3 to 5. What are we doing every time? 4 to 6.
Adds 2.
We're adding 2 to the term number, so it's n plus 2. And that would be the answer. You can always double check by expanding, like on a quiz or something. Just plug in 1, 2, 3 and try it and see if it works. So then the last thing is, what do these look like graphically? So this one is arithmetic, because you're always adding 2. And so I want you to see what that looks like. This one is what type of sequence? Geometric. And graphically, these are going to look different. So the first thing you should be wondering is how do I graph a sequence of numbers? What does that even mean? So the coordinates that you're going to graph are the x coordinate is the term number, and the y coordinate is the actual term. So basically you're doing, when you do any of these problems, you're doing n comma a sub n, and those give you the points. So for this one, 2, 3, the third term is 5, the fourth term is 7. So those are our points. What do you think you're going to get if you graph this? Well, let's see. 1, 1, 2, 3. Let's label so we know we're going by ones. 1, 1, 2, 3. The next one is 5, and then 7. We're growing by how much each time? 2. So it's a, what do the dots give you? If I kept going, it's a linear function. Exactly, it's linear. Now, here the interesting question is, does it make sense to connect these in terms of this problem? Is there meaning in between the points, or should I leave it as discrete? So it's just discrete or continuous. Do I connect them and make it continuous, or do I leave them and make it discrete? Is there such thing as a term 1.5? Okay, there isn't, because let's go back to the definition. For a sequence, the domain is consecutive integers. 1, 2, 3, 4. You can't have term 1.2, 1.3. So you would not connect those. So your graph would be left as discrete. So then geometric. Now we're going to plot 1, 1, 2, 2, and then 3, 4, and then 4, 8, and 5, 16. So let's go by twos on the y-axis. Maybe we'll use 2 squares. So it's okay to do different scaling on each axis as long as it's consistent. So I use 2 squares on the x-axis, and here I'm going to go by twos. 2, 4. I'm going to use one box is 2 units. 2, 4, 6, 8, 10, 12, 14, 16. So I'll be able to see this. So 1, 1, 2, 2, 3, 4. 4 jumps up to 8, and then we double from there. Every time we're multiplying by 2, right? That's the common ratio. So 5 jumps up to 16. So what function family is this when you're doubling every time? Exponential. Nice. So we had linear. Arithmetic is linear. Geometric is exponential.